A classical computer performs operations using classical bits, which can be either 0 or 1. Now, in contrast, a quantum computer uses quantum bits, or qubits, and they can be both 0 and 1 at the same time. And it is this that gives a quantum computer its superior computing power. There are a number of physical objects that can be used as a qubit: a single photon, a nucleus, or an electron. I met up with researchers who are using the outermost electron in phosphorus as a qubit. But how does that work? Well, all electrons have magnetic fields, so they're basically like tiny bar magnets. And this property is called spin. If you place them in a magnetic field, they will align with that field, just like a compass needle lines up with the magnetic field of the Earth. Now, this is the lowest energy state, so you could call it the zero state, or we call it, for the electron, spin down. Now, you can put it in a 1 state or spin up, but that takes some energy.
If you took out the glass from your compass, you could turn the needle the other way, but you would have to apply some force to it. You have to push it to flip to the other side. And that is the highest energy state. In principle, if you were so delicate to really put it exactly against the magnetic field, it would stay there.
Now, so far, this is basically just like a classical bit. It's got 2 states, spin up and spin down, which are like the classical 1 and 0. But the funny thing about quantum objects is that they can be in both states at once. Now, when you measure the spin, it will be either up or down. But before you measure it, the electron can exist in what's called a quantum superposition, where these coefficients indicate the relative probability of finding the electron in one state or the other. Now, it's hard to imagine how this enables the incredible computing power of quantum computers without considering 2 interacting quantum bits. Hello. Hi. Now there are 4 possible states of these 2 electrons.
You could think that, well, that's just like 2 bits of a classical computer, right? If you have 2 bits, you can write 00, 01, 10, 11, right? There's 4 numbers. But these are still just 2 bits of information, right? All I need to say to determine which one of the 4 numbers you have in your computer code is the value of the first bit and the value of the second bit. Right? Here instead, quantum mechanics allows me to make superposition of each one of these 4 states. So I can write a quantum mechanical state which is perfectly legitimate, that is some coefficient times this, plus some coefficient times that, plus some coefficient times that, plus some coefficient. So to determine the state of this 2-spin system, I need to give you 4 numbers, 4 coefficients. Whereas in the classical example of the 2 bits, I only need to give you 2 bits. So this is how you understand why 2 qubits actually contain 4 bits of information. I need to give you 4 numbers to tell you the state of this system. Whereas here I only need 2.